Eduardo González, Quantum Kirwan for Quantum K-theory.
And of course, something happened here.
Oh.
Can you?
I put infinity time. I'm sure I put infinity.
I don't know. It's my duty as the last speaker, and for you to actually thank the organizers for the beautiful conference. So thank you very much. I know most of you have to leave, so I'm going to keep this short. And so the whole idea, the talk is going to be just an announcement, really, of some work in progress that I have with Chris Woodward in the same line of the things that we've been working in the past 10 years or so, which is, a quantization of equivariant tools in some sense. And so the setup is as follows. So I'm going to take a projective smooth variety and with a polarization. So that sets, I have certain control of the instability condition, but I will tell you that in a moment. And then G is going to be a reductive acting on X. So there are two quotients that will play an important role. The quotient stack that you already know, have here plenty of it, and then the GIT quotient, which is given by whenever you have a polarization, then that gives you a semi-stability condition and the sense of Mumford, and then you just take the GIT quotient by taking the semi-stable points, semi-stable locus, and then divide by G. And in general, the setup it works in great generalities. So, for instance, for today, I'm just going to assume the quotient to be smooth, and but you can assume that this is a little Mumford stack, something a tiny bit worse. Or, for instance, we're thinking at the moment also, instead of having a projective smooth variety, so just allowing local complete intersections, for instance. And the two examples that I want to discuss today is essentially the Grassmannian, which is a GIT just given by the matrices, okay, of size k by n, and then divided by changing basis, and that gives you k-planes Cn. And toric varieties of all type essentially, but of course in the case that this is smooth, so I'm going to take just Cn, which is an affine space, and then divided by the standard torus. You may say, well, you ask X to be projective, and then you have an affine K. Also works in that case. Okay, so there is nothing to worry about. So the main motivation to study quantum K-theory for us is because we want to do complete and actually explicit computations. There are many works at the moment, like for instance, work by Okounkov and Molek, where they really want to extract explicit information of the quantum K-theory of quiver varieties, for instance. So this is more or less our main motivation. And that's what we're going to do. And so the theorem that I want to announce is, with the tools that I will present later on, is we can actually do an explicit computation of the quantum K-theory of both the Grassmannian and the quantum K-theory of the toric varieties, smooth toric varieties. And for the Grassmannian, it's just given by what you would expect. You have the universal and the universal quotient bundles over the Grassmannian, and then the quantum K-theory is just given by the Grothendieck, the total Grothendieck Chern class of the sum. This is a trivial sum, of course, and then twisted by or corrected by Q, right here. And this is just the Grothendieck Chern classes of the universal bundle. And for the toric varieties, is essentially, as you may imagine, you split Cn, which is the affine space that you have in here, in representations of the torus, okay? And then you break it in the representation, you attach some Novikov variables, and then the relations you will expect, which are the Batyriev relations, actually hold in this case as well. That's more or less what it's isomorphic in this case of two unchanged variables. I will explain that in a second. This is essentially given by the Batyriev relations. So the main tool that we use, and we have used in the past, to do all these computations, is the study of gauge maps. So remember that Gromov-Witten theory studies maps that go from a curve into the space, right? So this is more or less the stack that you studied. So if there is an action involved, and then you're studying maps into the GIT quotient. So in particular, the GIT quotient is a substack of the quotient stack, and then you take the equivariant lifts of maps that go into the GIT quotient, and then these maps that appear here just couples. There is a principal bundle with the curve that you have, and then a G-equivalent map. X. So they are given by these pairs. And so the technique is to impose a semi-stability condition in order to obtain a very good stack. And then once you have that semi-stability condition, then you essentially push the semi-stability so that the maps take values in the semi-stable locus of X. And then in that particular case, you can relate the Gromov-Witten theory of the quotient, the GIT quotient, with this Gromov-Witten theory, or the counts above for the equivariant maps. And so this is more or less what the philosophy of the theory is. So the semi-stability condition that we use is called Mundet semi-stability because it was introduced by Ignacio Mundet in this symplectic geometry side, and it generalizes semi-stability for principal G bundles, which was introduced by Ramanathan and the GIT theory of X, which is essentially introduced by Moffat. So the setup is as follows. At least the idea is I'm going to fix a degree, and in this case it's a degree in the quotient stack, and you take the homology of that curve. And then let's suppose that we can construct this moduli space of semi-stable objects, okay, of gauge maps, and then the evaluations. So if you add markings, and then let's assume that you can compactify, then you can take evaluations at the markings, and then you will have you will see that they can take values in the quotient stack in this way. And so the theory for the Gromov-Witten theory, as I was saying, for the GIT quotient is already well known, but the one that we can relate with gauge Gromov-Witten theory is not really just the Gromov-Witten theory. It's not all the Gromov-Witten theory affects mod G, but there's rather some sort of the one for the graph space. These are called graphs, because you are fixing a principal component of the moduli, and then you are letting and then you're asking that the degree of these maps is 1 in the portion that is over C, and then of degree D in the rest. And so that's more or less the theory. So we want to relate these two type of spaces. And so the question that arose is, once you push the semi-stability condition to infinity in order to relate these two spaces, they are not related on the nodes, but rather they have certain corrections. And these corrections are what some people already know. They account for some mirror symmetry phenomenon, and that's what the corrections are. So the corrections, we call them affine gauge maps, because what they are is essentially maps that go from the projective curve into the quotient stack, but with the point at infinity mapping into the semi-stable locus. Okay, so this is the way you connect the GIT quotient with the gauge maps. And then, so you can think of this as the semi-stability condition for these things. And we call them affine because you are only divided by affine automorphisms. So you're fixing the point at infinity. Okay, and so there are two evaluation maps. The evaluations of the markings go into the evaluation of the markings go into this should be X mod G to the N. So they take values in the quotient stack. And then the evaluation at infinity takes values to the GIT quotient. And so this is more or less the operation. So to do all these relations about these three spaces, the gauge maps, the usual stable maps that go into the GIT quotient with corrections in the affine gauge maps, we need a cobordism. And this cobordism is what we call, it's a geometric cobordism, and they are essentially gauge maps with an extra condition that tells you what type of semi-stability to use in each one of the components. And this is just given by X information, that you can think of it as being as an area form in the principal component of the curve that you have, and it's just given by a section of. So, for instance, if C is a stable curve with a principal has this principal component to be isomorphic to C that we are fixing at the moment. So you just take the dualizing sheaf, and then you projectivize it and take a section of it, and that's essentially this map is giving you a way of controlling the semi-stability that you have, and that tells you what type of semi-stability to choose. So you can think of this space as being composed by so the combinatorics of this thing is given by a stable map, but there is a root component that has this principal portion that is isomorphic to the original curve that you have, and then this scaling goes from infinity to 0, and the only way you can, and the semi-stability condition over here, or some condition that we impose, is that it can only go from infinity to 0, so it's some sort of decreasing in this way. But there is only one portion on which the scaling is finite. Okay, so this is one of the conditions that we ask. And so this is essentially the diagram. You can think of this. One of my collaborators, Pablo Solis, calls it a spider, because you have like the body of the spider here, and then the legs go down. You know, when they touch the bottom, then that's when the scaling is essentially 0. Okay, so then this gives you a natural geometric cobordism between all these moduli spaces. And so the theorem that one needs to prove, of the theorem that we have, is that there is a canonical morphism. By the way, this is a tiny mistake, I will tell you what. So if you take a point in this moduli space, so this cobordism, you just forget everything else, and then you just map to the scaling. Okay. And this has to be C here. So remember that there is a fixed principal component of the moduli. And so what happens is that this map, if you look at the inverse image at 0, the only thing that you get is the gauge maps. And as you push this scaling to infinity, so the point of infinity, then you will get all this combination of the maps that go into the GIT quotient, and then these correction terms that are affine gauge maps. And so the theorem is really this. Okay, so the fiber at infinity is given by this combination of 4 possibilities that you have. So you have all these correction terms that appear there. And so these correction terms in the classical literature in mirror symmetry is what they call the mirror map of given time. Okay, well, they will give you those combinations. And so this is completely geometric, so you can apply it to your favorite theory. The theory that I'm going to talk, I've been working on lately is Quantum K-theory. So Quantum K-theory is the same as quantum cohomology, in some sense. However, the only difference is that it doesn't have a divisor action, for instance, because there's no grading. You have to be a tiny bit careful how to do these things. But you still, since you have any projective variety, and then the moduli of maps has a perfect obstruction theory, then you can construct a virtual fundamental sheaf, which is not really a sheaf. There's an element in the derived category of coherent sheaves over the moduli space, and then you can just bundle all the numbers that you will get here. In this case, these are Euler characteristics, Euler numbers of taking. So if you take an element to the Quantum K-theory, you just multiply by itself several times. You correct it by the virtual fundamental sheaf, and then you take the Euler characteristic of this thing, and then that gives you an element in the integers. So that's very different from what happens in quantum cohomology, where all the Gromov-Witten invariants are rational. In this case, they are actually integers. So that's an advantage they have. So you bundle this into a potential function that is just a generated function of all these numbers, which are the K-theoretic Gromov-Witten invariants. And then you have also pairing. So once you have this potential, you can take derivatives. So the second derivatives, if you have two directions in the quantum K-theory, in the K-theory, then the second derivative gives you a pairing, which is voltic form in the direction of this value that appears in here. So that's another difference with quantum cohomology. In quantum cohomology, the pairing is not quantized. So the Frobenius structure in quantum cohomology has a pairing that is the same everywhere in all the fibers. In this case, the quantum product is quantized. So that's a big difference in the Frobenius structure. And then once you have this pairing, you can take the quantum product that's just being given by the triple derivatives that are being used. So it's essentially the same definition, but there are some differences. As I was mentioning, there is no divisor axiom. And therefore the computations get a lot messier than you would expect. So you can do the same thing with if a group is acting on your variety, for instance, then you get some equivariant K-theoretic potential, and you can also look at the graphs, and then you get the graph potential for the GIT quotient. And so the relation that we want to obtain is essentially that. So that cobordism, the geometric cobordism that I described at the beginning, will give you a diagram of this form. Okay, so this arrow here is all the potential that is given by the gauge Gromov-Witten invariants. In this side, you have the graph potential that is given by just the usual K-theory for the GIT quotient. And these correction terms, the corrections that appear by the affine gauge maps, is what you can think of the correction. So this diagram does not really commute, because as you move and you go in this cobordism, you may find some wall crossing terms. But essentially what this tells you is that if you use that cobordism, you can precisely tell what is the non-commutativity for this diagram. So they have some contributions from wall crossings. But anyway, so this map, as I was saying before, is the quantum Kirwan map, and it's just given by the pull-push construction. So you take a class in the equivariant K-theory, Quantum K-theory, you pull it back over the moduli of affine gauge maps, and then you push forwards that what you get using the evaluation at infinity, and then you get this map. It's a well-defined map, and the theorem, which it can be used by taking the polarization. The polarization so far is hidden in all of this, because I keep talking about the GIT quotient, and in that case it's hidden in there. But now it will play an important role, because essentially I didn't tell you what the semi-stability condition is on the gauge maps. That's where it's important. But if you take the polarization to go to infinity, then this diagram will commute, okay, and that's the important part. So, well, for the GIT quotient, that doesn't really matter. The only thing that you are varying whenever you increase the polarization is that the embedding that you will get, the linearization that you get, it just increases. That's the only difference. But for gauge maps, it does make a difference. Well, five more minutes. All right. So just very quickly, just to explain why when you go to infinity, things go to the GIT quotient, is the semi-stability condition for gauge maps have a contribution that comes from the bundle, as I was saying. So you can think of this as the term that comes from the Ramanujan semi-stability. So to define semi-stability for bundles, you need a parabolic production, and you need a one-parameter subgroup that, for which whenever you take the limit, the bundles exist. But let's suppose that you believe me that there is some sort of a numerical criterion for that semi-stability, and then there is another term that comes from the numerical criterion for the semi-stability of X, and that's the only thing that you have to do is essentially to take the sum of the two of them. But then if you increase the semi-stability for the target for X, then as that semi-stability increases, then this number will increase, will scale with that. So for the, that doesn't really make any difference if this term doesn't exist, but if the two of them pair, then as this goes to infinity, then this will affect the whole subject. So that probably, you can see that that's equivalent to killing this term, and therefore this one, that will force the points to be going to infinity. Okay, so I was going to talk about some compactification. I should just tell you that all these maps, all these moduli spaces are proper. I wanted to tell you that there is a relation with the quote scheme, but I will avoid that. Let me do an example, and then probably we'll finish with that. Okay, so let's consider the action of C star on C3, right? And so with the standard weight action 1, 1, 1, in that case, the GIT quotient would be the standard projective space with the usual linearization. And then in that case, let's take degree 1. So the bundle that you have to take, right? So it would be of degree 1, and so the associated bundle would be O1. So the equivalent maps that you take whenever you think of gauge maps are just sections of this bundle, which are just polynomials, right? Of degree 1, three pairs of polynomials of degree 1. And so it's essentially this moduli space is given by the regularization of this thing. And since there's no bubbling, you can just multiply by, if you add a marking. So the gauge maps with which are affine, right? So they must satisfy this semi-stability condition, and the semi-stability condition is that the evaluation at infinity should go into the semi-stable locus. The semi-stable locus is the non-zero points of C3, and so they have to obey this condition that appears here. So, and then with this diagram that appears here, you can essentially do computations already. So for instance, since X is already a vector space, then you can think of it as a C star representation, and then it splits as representations. It's three copies of the representation of weight 1. So it's already an element in the K-theory, the Quantum K-theory of the point. And so evaluation at 0, okay, so the evaluation at 0, the one that takes any polynomial of this form into P1, P2, and P3 will give you a section of the pullback of evaluation of 0 of x3. Okay, and so with that in mind, then if you want to compute the sheaf, the fundamental sheaf of that it will contribute for the counts that you are looking for, you just have to take all the classes just because this is a section, and you are taking the inverse image of the 0. Then that's just the Euler class of the pullback evaluation of this x1 to the cube. But this is a representation of weight 1, so then that Euler class is just 1 minus x1 dual cubed. And then since this contributes to the affine maps with 1 point, that tells you that this is essentially the image of or that this is in the kernel of the quantum Kirwan map of degree 1. And so that's how we obtain these relations. So this is the relation that appears in the projective, for instance, the projective space. Let me go back to the battery of relations. This one. So for instance, this one, there's no negative weight, so you just kill that, and then it will be just this 1 minus x1 dual to the third power equals q. Okay. And so that's how you do computations. We know how to do it in the toric case. So just very quickly for, I think I got prepared this, but so to get the relations in the, let's say for the Grassmannian, what we do is what is called abelianization techniques. So we know how to do it for the abelian quotient, so for toric varieties, let's say. And so since the Grassmannian is a quotient by a non-abelian group, then you can also try to relate what would happen if instead of that you look into the quotient by the maximal torus for GK. And that's not hard to see that the abelian quotient associated to the Grassmannian is just a product of PRs, and then we can compute certain function that is called the J function, which is nothing but the localization of the diagram that I had before. So how to say this quickly? So the diagram that related the potentials for the gauge potential, the graph potential, and the quantum K1 map can be localized in the case when the C is equal to P1. So you equalize it at 0 and infinity. And that gives you what is called the J and I functions on the nose. And these were introduced by Gimental. And then in that case, the quantum K1 map is essentially can be thought as a mirror map in that particular case. And so since we have this relation in here, the only thing that probably I should just mention quickly is that in order to get the relations in the quantum K-theory, you have to find differential operators that will kill what is called the J function. Okay, and since we know how to compute the J function with all this machinery, to cook up what the operators will be able to kill the J function is not that hard. And so in this case, well, I don't have a lot of time, but this would be, for instance, the differential operator. I don't have time to explain what all of this means, but we know exactly what would be the differential operator. What we need to do is to look at what operator kills the I function of the toric quotient, and then we cook up as some sort of symmetrization operator that will kill the J function. It will make it vanish, and in that way we obtain relations. And just those relations happen to be the ones that you want in order to prove that the quantum K-theory has the presentation that you want. And that's more or less the idea. So I think I'll stop there so that people can go to the airport.
Questions for speaker?
One question. Can you do something like that? I think you can do something like that for a classical G mod P quotient with the...
Oh yes. I think it's proven, but only in the past like 20 years, I would say. Even the presentation for the K-theory of toric varieties has been done no longer than 20 years. But yeah, you can do the same thing. Yeah, essentially classically you can, but that's not what we're after. Yeah.
Any more questions? No, that's knowledge. Eduardo? Yes.